Chapter 4, we're going to talk about moments. Now, a moment about a point, it's two words, but it's one word now, is really the effect that occurs when a force acts some distance at some distance from the point. So let's say we have a point here, point O, and then we have a force over here. Extend the back tail a little bit, and you'll see why. Extend the back tail, say this is force A. Well, the perpendicular distance to that force, so it's really the shortest distance to that force. The perpendicular distance to that force, we usually label this as D, and we call that our moment arm. Well, we can say then that the moment about 0 of A equals some force, let's call it the magnitude of A, times a distance. So let's say that the magnitude of A, let's say it equals 10, and the distance here is equal to 2, let's say 2 meters, and the magnitude of A is 10 newtons. Then we can calculate our moment about 0 as 10 times 2 equals 20 Newton meters. We can, of course, have a situation where we have multiple forces around a point in any direction. We're kind of looking at 2D situations right now. We'll extend this to 3D. Then each of these will have a moment arm, perpendicular distance. We change the color of this one. We're not going to go back at this point though. Perpendicular distance and perpendicular distance. So if this is force 1, this is force 2, say this is force 3, we could say this is distance 3 here, this would be the distance to 1, and this would be the distance to 2. So we can have a resultant moment then. So the resultant moment about O, call this a resultant moment, equals the sum of all moments about O equals the sum of all forces times perpendicular distances. And this is, right now we're just talking about magnitudes here. So let's define a convention. Let's say that the moment is, let's add another one in here too. Let's add another force, because I want a force going in the opposite direction, like this. We'll call this F4, because that can happen too. Then the perpendicular distance here is that distance. Let's create a convention and say that counterclockwise is positive for our moments. So if we're going to sum moments for a resultant, then we'll follow this convention. So may as well put this over here so it's out of the way of everything. So we end up with force 1 times d1, and that's going to be a positive number. It's heading in the positive direction. Plus, we'll go force 3 d3. I'm just going to go around in a circle so I don't miss one. Plus f2 d2. But this one's going this one's going clockwise. So we're going to have to subtract that. Minus f4 d4. And we can assign magnitudes and distances to these values here. And so we can get a numerical answer here. Okay, let's do an example. Say we have a beam set up kind of like this, where A is positioned here at kind of like the origin, and B, the point B is in the middle of this beam, which is 0.5 feet. And the rest of the loading is as shown here. We want to calculate our resultant moment at A. So let's just start working on our moments. So each of these forces is going to add to our moment. So let's say the moment of, let's give these letters F1, F2, and F3. So the moment of F1 about A equals, keep in mind any direction like this we're going to take as positive, equals 375 times 8, or 3,000 pound-foot. And this is causing a clockwise rotation, so that's going to be negative. It's opposite to our convention. So instead of writing negative 3,000 pound-foot, which I could do, well, I'm going to do, I suppose we could write it as minus 3,000 pound-foot. But if I was going to have this as a result, I would probably put this as 3,000 pound-foot, and can we slide over a bit? 3,000 pound-foot, and I would draw the arrow this way to indicate that that's the direction of it. So if that was a result, I probably would do that instead of using the negative sign, just so there's no confusion. Okay, the moment of F2 about A. So F2 has two components. So one component is here, the perpendicular to A, and the other component is in this direction. So the force is applied here, so it's really in this direction along this line. And you can see there is no moment arm because that goes through A. So we only have to worry about the first component. So the vertical component, and that is proportioned as 4/5 of 500 times our moment arm of 14. I always forget to add the moment arm, and that's an easy thing to do for everybody. So 400 times 14 is going to be 5,600 pound-foot. And again, that'll be acting in the negative direction. So if it's on its own, we can put a negative. But if we were going to display it as an answer, I would still write this way without a sign on it. No confusion. The reason I'm having signs here is because I wanted to sum my moments about A for a resultant. And so now we get to the 160 pounder, and you'll see that this has a component in the vertical direction, sure, but there's also a component in this direction, and even though it's small, there is a distance between, a perpendicular distance between that and, because this component is actually acting up here along this arrow, there is a small perpendicular distance there, whereas this component in the vertical direction has a very large distance. So our first effect is the vertical, so I'm going to go minus 160 cosine of 30 times a moment arm of 19, and then this is actually going to rotate positively. So we'll have positive 160 sine of 30 times 0.5. And as our last step, let's just sum all those together to determine our resulting moment at A. So minus 3,000 minus 5,600 minus 2593 equals minus 11,193, and I'll just represent it as 11,193. We need units on these, pound foot and pound foot here. So now we're going to talk about cross products. And cross products are another type of vector multiplication. We have dot products we already did. We're going to cross products are also, and we represent them by this big cross here. It's not exactly a multiplication sign. It's a cross product, and we define this as the magnitude of A times the magnitude of B sine of theta, very similar to the dot product, except we're going sine of theta, but the difference is that in a cross product, our result's not a scalar, it's actually a vector. And even though we're taking two vectors and we're crossing them, we're going to end up with just one vector. And it's going to be pointed in a different direction. It's going to be pointed in a direction that's perpendicular to both. So this unit vector is going to be perpendicular to both A and B. So if you can think any two vectors makes a plane in space, if we go perpendicular, then we're going to be pointing outside the plane that those two vectors make in one direction or another, for example.